So today we will start our recording for lecture number 7 of the linear algebra series that we have started. So today we will cover product of vector spaces and a quotient of vector spaces. Last time we have discussed isomorphic vector spaces and the special scenario of the linear maps between V and W vector spaces, and then we just consider W to be equal to V, and then we call those maps as linear operators. Now let us define product of vector spaces. So suppose that we have collection of vector spaces over a field over our field F, and the product here is denoted the product of V1 to Vm is just defined by V1 up to Vm. This noted this way. So this is just defined as the collection of the ordered M tuples, or ordered listing of V1 to Vm. So first, our V1 is an element of V1, and then up to Vm, an element of Vm here. And then how do we define addition? So addition is as follows. So if we have U1 up to UM, then we add this with V1 up to Vm. We just have the U1 plus V1 up to UM plus Vm. And then with our scalar multiplication is defined as follows. So we just have to multiply each components of the ordered list by lambda. For lambda in the field F, lambda times this ordered list U1 to UM it's just U1, and then lambda UM here. Now, because we have defined vector addition or addition between elements of the product space and then scalar multiplication on the product space, we will associate a structure on this set, namely, getting ahead myself, it's just a vector space also. But before that, let us give an example of a product space. So suppose we have the polynomial over R of degree at most 2 multiplied by, or the product together with R3. So this is a list of length 2. So this is our V1, and then this is our V2. They are vector spaces. So there are only 2 vector spaces. And then the first item is just is an element of the polynomial ring of degree at most 2, and the second item should be an element of the ordered triple. So for example, an element, say U of P to R. Okay, I have one R here. Across R3 is here, if we have U here, an example of an element of this ring, this product is just the first component is a polynomial. So let's say it's just 5 minus 6x plus 4x squared. So this is an element of this polynomial vector space, and then the second element will be ordered triple. So we just have like 1, 2, 3. So this one is an element of this, an element of this one. Now, as I remarked earlier, let me state this as a theorem. If we have V1 to Vm vector spaces, then we have V1 up to Vm, the product of vector spaces is also, this is over F, also a vector space over our field F. So the proof here is easy. You just check each element, each axiom of the vector spaces. Vector space axiom is satisfied by the product defined above, and then together with the operations defined above. Okay. Let us now proceed. Look at this example. This example will give us a nice theorem. So is R2 cross R3 equal to R5? The answer is no, because what's an element of this? An element of this is just 1, 1, and then here 1, 2, 3. An element of this is of like 1, 2, 3, 4, 5. They are not equal, but are they isomorphic? So the answer here is yes. And the answer is yes. So suppose that we have the vector R, a vector in R2 cross R3 is of the form x1, x2, and then x3, x4, x5. We can, of course, our x's here are in R. We can map this vector V, map V into this one, V, x1, x2, x3, x4, and x5 element of R5. Yeah. This is this map here, say M. M is an isomorphism of vector spaces. And this is just a homework. If you want, you verify when you study. Okay. So the isomorphism is natural, as we should think, as it's just relabeling. So as we have before, we can think of vector space isomorphism as just the vector space is almost, they are the same up to relabeling. Okay. So now let us consider another example. Here we are to find the basis of our vector space P2R cross R2. So for the first element, P2R, we have, this is of degree, of dimension 3, right? This is of dimension 2. What to expect is the dimension of this product R2, R P2R cross R2. So what's the dimension? So let us consider a basis here of P2R. So a basis of, let's say this is our U. of U is maybe uh, yeah. For the first one, we just have one, and then the first element is a polynomial, and the second element is um this, and then this one, x here, and then 0 0, and then x squared 0 1, and the other one is 0 x squared 0 0, and then the other one is 0 1 0, then the other one is 0 0 1. So here we can check that this set, let's call this star, is a basis of U here. Okay. So how do we generalize this fact? Okay. Let us state this as a theorem. If V1 to Vm are vector spaces, of course they are finite dimensional vector spaces, then your V1 cross Vm is also finite dimensional vector space, and your dimension of V1 up to Vm is just equal to the dimension of V1 plus the dimension of up to the dimension of Vm. Okay, so how do we prove this? For the proof here, uh, shows a basis of each Vi, Vj. Okay, for each for basis of of Vi, Vj, consider, let us call this U. Consider an element, consider the element of U that equals the basis vector in the jth slot and 0 in all others. Okay. Okay. Then if you collect them, those vectors, and then if we, this collection, this list or collection is a basis. Okay, so this is to verify, but this is clear from the context, so that we have for this collection, so the length of the bases is equal to the length of bases is dimension of V1 plus the dimension of VPM. So as an example, let us look at this one. So for for each basis, this is based on the first collection. We have 1x and x squared is a basis. That's 1x and x squared is a basis for P2. And then you adjoin all else 0. And then here on the other one, 1, 0 and 0, 1 is a basis for R2. And then all the others, you just put 0. So that's the rough sketch of the proof here. Now we go to some theorems on products and direct sums. So U1 to UM subspaces of V define a map that gets an element of U1 cross UM into U1 plus the UM. This is the direct sum, this is the product, and then defined by, here we get an element of U1 to UM, and then this is just equal to a U1 plus UM. And then what is the result? The result is that U1 plus UM is a direct sum. Okay, direct sum if and only if our this one is injective. Okay, let us provide a sketch of the proof here. So if this is injective, then injective, what can you say? The 0 is just, this is true if and only if 0 is just U1 plus UM, and then UJ in UJ, and each U sub J is equal to 0. This is by being injective. Thus, this is if and only if. Thus, which is true if this is a direct sum. So the claim follows by the definition of direct sum. Notice that this is just a sketch of the proof here. And then I will consider also another theorem whose proof I will leave as exercise. So we have V, another collection, the same U1 to UM subspaces of our vector space V over field F. Then your U1, the sum U1 to UM is a direct sum if and only if another condition is the following. Not this is the first condition. This is a direct sum if and only if the dimension of this sum U1 to UM is equal to the dimension of U1 plus the dimension of UM. So here in this theorem, it uses the theorem number, the theorem above, and then follows by combining the theorems, previous two theorems. So I leave the proof as reading. Okay, so we will now go to quotient space, quotient of vector spaces. Okay, so first let us define the this notation. Suppose V is an element of V and U is a subspace, of course, of V. Our field here is F. Then your V plus U is just the collection defined as U plus V, or in our U here. Okay, let us fix the notations. V plus U, wherein our U is an element of the subspace U. For example, we have U here be defined as X and 2X. So these are element of R2, and X here is an element of R. If you look at this one, so if your X is just X and your Y, your second component is 2X, then this is just a line through the origin. Okay. Okay, a line through the origin. So this is a line through the origin. So this is, let's say this is 10, 20. Okay. So U is a line through the origin, and then with slope 2. So 17 plus 20, 1720, so 1720 plus U is a line in R2 that contains the point 1720 with slope 2. Okay. Now we define an affine subset and the notion of parallel. First, affine subset of V is a subset of the form V plus U for some V in the vector space and some subspace U of V. For an element V in the vector space V and U subspace of V, the affine subset V plus U is said to be parallel to our subset U. So V plus U and U are parallel. For example, your in above, all the lines above, all lines with slope 2 are parallel to our, say U is just 17, 20, V plus U is 17, 20 plus U. Where Our U is the line with slope 2 through the origin O. Okay. So another example is in R3. Consider the ordered triple where X and Y are in R. Affine subset of U are the planes in R3. So affine subsets, let us consider this of U here are planes in R3 that are parallel to the XY plane. This one is XY plane. Okay. Now we define a quotient space. Can U subspace of V? The quotient space, quotient, wrong spelling. Quotient space of V modulo U is the set of all subsets of V parallel to U. Okay, let us note this annotation. This is just V plus U, where U here is okay. V here is an element of the vector space V. Example, I will give maybe the previous example. So if our U here is just X to X, X in R2, in R, then this R2 modulo U is just the set of all lines in R2 with slope 2. And then the second example is if we have R3 modulo the U, and then if U here is just X, Y, 0, X and Y in R. So this is equal to the planes through the origin parallel to XY plane. Okay. Let us have some theorems. The proof of this theorem is very easy. We follow with V and W elements of V and U subspace of V. The following are equivalent. Number 1, V minus W is in U. Number 2, our U plus V plus U is equal to big U. Here, this is big U, equal to W plus U. And then number 3, V plus U intersection W plus U is not empty. Okay. Right. I will leave the proof for exercise here. I will just prove um letter C implies A. Suppose that C holds. So U plus okay V plus U. V plus U is intersection W plus U is not empty. Let us consider U1 and U2 element of U such that our V plus U1 is equal to W plus U2. Okay? Hence, U minus V minus W is equal to U2 minus U1. And then these are element, which is an element of U here. Thus, V minus W is an element of U, showing which is our A. So the other connection or implications are left as an exercise. Now, let us define some operation on this quotient. Let us define an operation on the quotient. So if we get for V modulo U, so if we get we define addition. So what are elements of V mod U? So V plus U here, add with W plus U. This is just V plus W plus U. And then also, if we have lambda, U plus, wait, let me use the letter V plus U. So this is just lambda V plus U. So this is for lambda in the field and V and W in the vector space, not vector, in the quotient surface V mod U. So because of this, we have the following theorem that V mod U is a vector space. It's a vector space, of course, over the field of the ground field F here. All right. The axioms, the proof that this is a vector space, just check each vector space axiom. So this is easy. You just check that we have the zero element, we have all the other axioms of vector space. Now we go to an important theorem. Before going to the important theorem, let us consider some preliminary definitions. Let's define the map, the quotient map. So the quotient map, okay, wrong spelling again. Quotient map I is the linear map by getting an element from V and with the results in V mod U. And then this is defined by phi of V is equal to V plus U. This is for all V in the vector space. Of course, U here is a subspace. Okay, subspace. So that's our, of course, this is to verify that pi is a linear map. A well-defined linear map. So let us state an important theorem, and that is the dimension of V modulo U is equal to the dimension of the vector space B minus the dimension of our vectors subspace U. Okay, let us quickly prove this. Okay. The null space of pi is equal to U. Thus, our range of our pi is V my modulo U. And then, of course, this is fundamental theorem implies that the dimension of V is equal to the dimension of U plus the dimension of V modulo U. And this is okay because this the rearranging we get the desired equality. Okay, another theorem. Oh wait, define first. T tilde is T tilde. Okay, let us define T tilde. Okay, erase. T an element of the T a linear map from B to W, and then T tilde is just V modulo the null space of our T to W, and then T tilde of V plus now T is equal to T of V. All right. So if you have a linear algebra, it's just the first isomorphism theorem. I mean abstract algebra. This is the first isomorphism theorem. So this is the important theorem on null space and the range. This is the first isomorphism theorem. The first isomorphism theorem. Let T be an element element of the set of linear map from B to W. Then number one, T is a map, a linear map from V modulo the null space of T to W. So this is clear. Number two, T tilde is injective. Number three, the range of T tilde is equal to the range of T. And number four, the dimension, okay, not yet. The vector space B modulo the null space of T is isomorphic to the range of T. So this is the first isomorphism theorem. So suppose that we get a vector space V, and then we get a V to W, and we get here that may delay the presentation of that for later. So for the proof for number one here, this is easy. Number two, T tilde of V plus null T is just equal to 0. Then T of V is equal to 0. That means V is in the null space of T. Hence, your V plus null T is equal to 0 plus null T. This implies that this means that our null T, that our null of T tilde is what? Is just 0. Hence, thus T tilde is injective. And number 3, this is easy by definition. And number 4, this is again easy by applying our number 2 and number 3. Okay, that's it for our null space and the range of T tilde. Okay. And then W, we get the mapping from V modulo the null of T, and something like, let me verify this commutative diagram, but I'll draw that next meeting. But for now, let me end the recording here and state what's coming up next. Up next, we will consider the concept of duality. This is a bit long. We will consider the transpose of matrix. And yeah, maybe we will spend 2 meetings for duality and the transpose of matrix. So let me end the recording here.